Hi everyone, welcome to Chemistry Insight. In this particular video, I'm going to talk about a Favorskii rearrangement. Now, what is meant by Favorskii rearrangement? What is happening in case of Favorskii rearrangement means, in this case, what will happen? Alpha haloketones, alpha haloketones will undergo rearrangement with alkoxide to give an ester. So here alpha haloketone is there, plus it will react with alkoxide. Alkoxide ion, it can be sodium or potassium with a cation can be there, and what it will give, finally it will give an ester. I will give an example, and afterwards I will discuss a detailed mechanism of Favorskii rearrangement. Now, suppose here only one alpha hydrogen I will be considering, and here carbonyl group is there, and here I have carbon, and here halogen. Suppose X I will take, and R and H is there. In this case, we have two alpha hydrogens to the carbonyl group, that is this hydrogen as well as this hydrogen. Now, to this we will add a base, that is sodium methoxide I will take. Sodium methoxide, or in methanol, correct? In methanol, this is a negative charge. OMe will has to abstract a acidic proton. More acidic proton is present over here, but attack at this particular hydrogen, like if it abstract this particular proton, the negative charge will delocalized over here and there is no use. It is reversible reaction. But what we want a irreversible reaction. That's why this, whatever the methoxy group is there, it has to abstract this particular proton. Finally we will get here R will be there. Final product I will write over here, and afterwards I will discuss about the mechanism. Here finally I will get R, here CH2, then Cr2, then C double bond O, OMe. This is the final product, and now we'll discuss about mechanism. Mechanism is very interesting over here. We'll discuss about it. Suppose here I will just write a acidic proton like this, and here carbonyl group is there, and here carbon, and here one halide. X only I will take, and another hydrogen and R group. Now what will happen? This OMe is there, OMe minus. It will come and abstract this proton, and finally this electron will shift like this, and finally negative charge will be coming on oxygen, and finally we will get it as R2. Then here carbon is there, and carbon carbon double bond came, and here like this, and O minus, enolate, it will create enolate, and here carbon, and here X and R and H is there, right? And in the next step what will happen, this negative charge will come back like this, and whatever this enolate is there, it will abstract this particular carbon, and whatever the halide is there, it will leave as a leaving group. This is the rate determining step, and finally we will get it as a three-membered ring, that is here carbonyl group is there, and here we have carbon and R2 is there, and here we have carbon. It all this whatever the reaction is there, it is going through SN2 reaction. That here I will get R, and here H, right? We will get this one as three-membered ketone as an intermediate, and what will happen in the next step is we have methoxide ion. So many methoxide is there in the medium. Whatever this is there, it will just come and attack this particular carbon, because it is a three-membered ring with a carbonyl. it is making 120-degree angle, right? Which is very strained position it is there. That's why this reaction will happen very quick. Then what will happen, this electron will shift like this, then we will get a tetrahedral intermediate, like here carbon is there and three membered ring, just I will write like this, and here one R I will show like this, and here one R and second one, and here what will happen, O minus, this is a tetrahedral intermediate which is highly unstable in nature, and again what will happen, this whatever the negative charge is there, it will come back like this. Now we have two options, either this bond can break or this bond can break. Here what will happen, suppose I will write it as a first case, if this bond break, then we will get a product like here carbon and here R2, over here minus negative charge is there. Then again this bond I'm writing over here carbon, and to this one hydrogen and one R is there. Then again I have to write like this, here OMe is there. Then what will happen, in the media we have methanol. Methanol is also acidic in nature. Then what will happen, this whatever the negative charge is there, it will abstract the proton, and finally the whatever the methoxide group is there, it will leave. Then what we will get a final product, just we have to add a proton over this particular carbon. That's why we will get this particular product as this particular product we will get. In this case, suppose if this bond breaks, I will show it by a black color only. Suppose if this bond breaks, then what will happen, I have to write this particular as the first. That's why I have to write this particular carbon over here, one R is there and one H is there, then a negative charge, and again this bond I am writing over here, and here Cr2 is there, then again C double bond O, then OMe. After protonation we will get it as R CH2, then Cr2 and C double bond O and OMe. We will get this product as well as this product, but which is the major product in among these two, this will depends on what about the nature of this substituent, that is R. If R is more electron withdrawing, we will get a one product, and if it is electron donating, we will get a different product. This reaction we have to explain by taking certain example. First of all, I will take one example as suppose if I take Me is there and here C double bond O. This is simple acetone with alpha halogen I will take. Here carbonyl, like suppose carbonyl group, and afterwards CH2, and over here suppose chlorine is there. A simple example I will be taking in order to understand. Okay. Okay, here I will write not methyl because it is symmetrical, it will become here CH2 and CH3 I will take like this. Then if we add sodium methoxide in methanol, what is the final product we will get? This is a predicted product, and finally we have to work out on mechanism. First of all, abstraction of proton has to be done with the alpha. This is acidic protons. Here also acidic is there, but there is a no use, but because it is a reversible reaction, that's why here I will write it as CH3 and C carbonyl. Here what I can show it directly because we already worked on mechanism. Here what is happening is OMe will, this methoxide ion will abstract this particular proton, then again like this, then what we will get, double bond and one hydrogen is there, and C, suppose I will write O minus like this, then here CH2 Cl, suppose I will write like this. Then what will happen? This enolate, whatever it is there, it will just attack in SN2 fashion, and the chlorine will leave as chloride, leaving group. Then here CH2, we will get a 3-membered ring, that is CH2, then C, and here carbonyl group is there, and here CH2, then here one, like this we will get. Now we have two options when the methoxide ion attacks and generation of tetrahedral intermediate is there. Suppose if it attacks over here like this, we will get, I will write like this, sorry, tetrahedral intermediate I have to show over here, that's why I have to write O minus, and here OMe is there, and here normal, here CH3 is there. Correct? I hope this is the tetrahedral intermediate. Then we have two options, that is, if suppose if this bond comes like this, if suppose this bond breaks, then what will happen? Here CH3 is there, and CH2, here negative charge will be there over here. This bond breaks, then again I have to count this carbon. Here CH2 is there, and finally I have C double bond OMe, like this. Now this is one like product with a negative charge. Then again, if this bond breaks, I will write a different product. Suppose if this bond break like this, then I will get it as, here CH3 is there, then again okay, this bond will come like this, then this bond goes like this. Here the generation of, okay, I have to write, then first I have to write this particular carbon like this. This one I have to write it first, that is CH2 minus, then again this particular carbon I am writing over here is attached to CH3, and one hydrogen is there like this, then again it is attached like this, C double bond O, then OMe. Correct? This is the two product with a negative charge we will get like this. When we observe over here, it is a secondary carbon which is carrying a negative charge. Over here we will get a primary carbon carrying a negative charge. Among these two, we know that this product, whatever the primary carb anion is there, this is the more stable, because when we consider the stability of carbanion, carb anion, we will write it as a primary is more stable compared to secondary, and tertiary is the least stable. This order we have to remember. That's why we will get this one, this product as the major product. This one as the major product. This one also we will get, but it has a minor product we will get. Then we have to final product, we have to write it as like this. Negative charge we will remove that, and finally we will write it as, okay, here only I will just modify that. Here I will have to write CH3. Correct? This is the major product. Over here CH2, this one as the minor product. Now we'll discuss what is the application of Favorskii rearrangement. Two isomeric alpha chloroketones gave exactly the same product on treatment with methoxide. Both the reaction will have the same intermediate. Now I will take one example over here from two different isomeric alpha halocarbonyl compound, how we will get a same intermediate which can be applied in Favorskii rearrangement. Suppose this is a particular compound, and another compound I will take it as, here phenyl is there, and here like this carbonyl is there, and here CH3. Then here chlorine is there. Here chlorine is attached away from the phenyl group, and here towards benzylic carbon is that to that chlorine is attached. These are the two isomeric alpha chloro ketones, we can call it as. Suppose if we add OMe, that is sodium methoxide in methanol, and here also sodium methoxide in methanol, we will get a same intermediate, that is we will get it as pH, and here we have this particular carbon, and here like this we will get. You can try the mechanism, it's very easy. Then again for this particular in cyclopropanone ring, again the attack of methoxide ion will takes place like this, and the generation of tetrahedral intermediate is there, and what we will get, we will get it as here O minus, and here OMe, and here phenyl is there. Now when this bond comes back, that it forms a carbon and oxygen double bond, it is very stable. Now this bond will break because it generates a benzyl carb anion which is very stable. That's why we have to write like pH is there, and again we have to write it as here pH is there, which that particular carbon contains CH minus, and again CH2 and C double bond O and OMe. Again this one get protonated. Finally we will get pH, CH2, CH2, COOMe. This one as the major product. Then again different example, if we want to take suppose cyclohexane like this, cyclohexanone with the alpha chlorine. Here also we will get, this is a different example, we will get it as a negative charge will be generated over here, correct, and again this negative charge will attack this particular carbon, and nucleophile, that is the leaving group, will leave the moiety, and finally we will get it as a three-membered ring. This is somewhat like bicycle ring we will get, and here we will get it as C double bond O, correct. This is a bicyclo compound, we will call it as. Then attack of methoxide to this particular carbonyl group will takes place, and the generation of tetrahedral intermediate, and finally we will get it as like this, O minus is there, and here OMe, right. When this carbon and oxygen will make double bond, either this one can break or this one can break, both are symmetrical in nature. Finally we will get it as a five-membered ring like this. As it is, I am writing just to understand that here I will get C, this carbon I am writing over here, which is attached to carbonyl group like this, and again over here OMe is there. This is the major product we will get. This is the major product. Only one product we will get in this case, because it is symmetrical in both the carbon atom. Then this is an example of ring contraction, right? Because in this case what happened, here six membered is there, finally we will get it as a five membered. Another example we will be taking like this. This is cyclobutane ring, and here carbonyl group is there, which is attached alpha position. We will get a chlorine like this, and finally if we treat with a methoxide ion with in methanol, we will get like this. Mechanism you have to work out, it is very easy. After working the mechanism, we will get a tetrahedral intermediate which looks something like this. Here O minus is there, and finally we will get like this. Here what will happen? We will get ring contraction again, and we will get a three-membered ring over here, and which is attached to carbonyl as like ester, like this. This is the major product. Now we'll move on to the next thing, that is when, suppose here one example I will take. It is an very interesting molecule, which is here carbonyl is there, and again here I will take like this, and here chlorine is attached. Suppose this is the given reactant, and with potassium hydroxide, this one also can act as a base, that is OH minus will generate over here. It will abstract this particular proton, and finally we will get it as a three-membered ring. After this attack to the carbon contains this chlorine, the chlorine will eject from this, and finally we will get a three-membered ring which look like this. Here carbonyl is there, and here again like this, symmetrical it is. Now after the attack with water, I will take here as water. What will happen is this water molecule will attack over here the lone pair, and finally we will get a tetrahedral intermediate. I will be just writing over here like this. Yeah, here O minus is there. After the removal of one proton, I will just write it as OH like this. After like this, this bond can break, or this bond can also break. This is symmetrical in nature. Finally, I will get a carboxylic acid which can attached over this particular carbon atom. This is the final product we will get. Suppose if there is a no alpha hydrogen, what with no alpha hydrogen can be carried out a Favorskii rearrangement? We will try by taking one different example. If suppose no alpha hydrogen is there, then if we add a base, whether we will get a Favorskii rearrangement or what. For that I'm taking one different example. Suppose here chlorine is there, and here carbonyl group to which a phenyl group is attached like this. If we add a base, suppose OH minus, if there is no acidic hydrogen is there, then what will happen? This hydroxide ion will attack this particular carbonyl compound, and finally we will end up with a tetrahedral intermediate. Finally we will get it as like this. Here nitrogen, it is all the remaining things, whatever it is there, it will unaltered. And here I have chlorine, and here carbon to this O minus is there, and here OH, and here I have phenyl group. Now what will happen when this electron will come back to form carbon and oxygen double bond, and here what will happen is this whole phenyl group is there, it will migrate towards this carbon, and finally the halogen will leave. It will look like benzoic acid, like benzoic type rearrangement we will call, and finally we will get the product as like this. Here methyl group as it is like that, and here phenyl group is attached over here with a here I will write Cl minus, and here C double bond O and OH, right? We will get this one as the major product. This is a Favorskii rearrangement which involve a benzylic type rearrangement. Um, this is a different type of example, and suppose I will take a different example, that is when a cyclohexanone is there, and over here I will write like this allylic bromide, like this particular moiety if it is there. Again here if I add OMe, if I add, then we will get up to 3-membered ring. I will write like this, and afterwards I will show the mechanism. Finally we will get like this, correct? Okay, in this case what will happen is, here generation of enolate we will write like this, correct? Here O minus enolate we have to write here. Finally we will get a negative charge direct attack, like that we can't able to show. That means we have to, negative charge has to delocalized onto the oxygen atom, because this is the most stable configuration. Enolate ion we have to show in mechanism, and here bromine is there. When this one will return back to form carbon and oxygen double bond, this enolate, this electron will attack over here, then this one will shift like this. Finally it will bromide ion will leave, and we will get a bicyclic compound which is like this, and here single bond is there, and over here double bond like this. Here same carbon carbon, sorry, carbon and oxygen double bond carbonyl group is there. To this if we add methoxide group, finally we will get a product which is a 5-membered, and here the same group like this it is there, and here C double bond O OMe. This is the final product we will get. The negative charge, this bond will break over here, because the negative charge over here is delocalized by this allylic group. That's why we will get a product like this. Now, stereochemistry, if you want to take, I will discuss in this particular slide. Suppose this is the example I am taking over here. This is carbonyl group is there, and here like this I will show like this, and here also like towards us we will show a tertiary butyl group like this. Now if we add a base, that is OMe, which one we will get it as a product? To this we have to write a cyclohexane conformation like this, and here double bond we have to show like this, and this is above, correct? That's why we have to write it above like this. And here also chlorine is there to the second position, that is also above, means we have to show like this, correct? Now to this particular compound we have to confirm, like we have to convert this to chair form, then only we have to carry out the reaction. Now the negative charge will be generated on this particular carbon. I will just write like this negative charge over here, and attack of this negative charge to this particular carbon is taking place, because this whatever the negative charge is there, see I will just try to write like this it is there. I will just elaborate. I'm writing over here, this is Cl is there, this is anti-bonding orbital of this, whatever the negative charge is there, it is anti-periplanar to this particular carbon and chlorine, this bond, this is anti-periplanar. If the negative charge as well as whatever the anti-bonding orbital is there, if that one is anti-periplanar, like 180-degree, then the reaction will take place. That means the negative charge can go into this particular orbital, and the chloride ion can leave that moiety. If that one is not anti-periplanar, this reaction will not take place. In this it is anti-periplanar, that's why the reaction will takes place we will get a product as like this. Here it is there, and here carbon like this. Now what will happen if this one is a bicyclic compound. Finally, attack of OMe to this carbonyl group, then again the generation of tetrahedral intermediate, all the same thing will happen over here. Finally, we will get a product as 5-membered ring, correct? We will just write like this. This one is a 5-membered ring. Over here, I will write it as a C double bond O, OMe. This any bond can break, either this, because it is symmetrical in nature. Because of that, we will get a product like this. Here, hydrogen is there. This is the product. Suppose here, if I take, I will write it in chair form like this. Suppose here if it is there, and negative charge over here, again here carbonyl group and here tertiary butyl group. If it is there, this negative charge and this whatever it is not, this is anti-bonding, that is sigma star we can write. It is not anti-periplanar to each other, that's why no reaction, because here we can't able to observe any product. That's why we have to write it as no reaction is there in this case. I hope Favorskii rearrangement is understood by you people, and in the next video I will be taking up with a different name reaction. Thank you very much.